Hey guys, we're going to work some of these practice problems. I'm just going to start at the top, pressure practice problems. Going to do number 1 first. What force is applied by atmospheric pressure to the surface of an island 3 kilometers by 5 kilometers? So they give you 3 by 5, that's the area. And you got to use atmospheric pressure here. So, here's my little sketch pad. The area is 3 kilometers by 5 kilometers, or, look at me, 3,000 meters by 5,000 meters. You got to multiply those two together to get your area. Whatever that is. So you can do it here in a minute. And then the second thing you're going to do, pressure is equal to force divided by area. Right? And if you move that around, you can solve for force. Force is P times A. Right? So the idea here is you can take atmospheric pressure, right, and multiply by whatever the area that you got from up here, P times A, and that'll be your answer. So there you go. All right, and the answer to that first one here, 1.5 times 10 to the 12th, and that is force. That's in newtons. Okay, there you go. All right, number 2. Something about a swimming pool. What's the gauge pressure and then the total pressure at the bottom of the swimming pool? It's 4.5 meters deep. It's about 4.5 meter sticks deep. It has a diameter of 2 meters. They tell you what atmospheric pressure is in pascals. And here's the density of water. These are the answers. So to do this, gauge pressure is rho GH. Rho, of course, is density of the fluid. So there's 1,000 for water times 9.8 times the depth of the pool, and 44,100 is your gauge pressure. To get total, can't write very fast. Anyway, you take your gauge pressure and then you add atmospheric. You take this and you just add atmospheric pressure to it, and you get a much bigger number. And there you go. Done. All right. Third and final one of the pressure practice problems. This has to do with what is the gauge pressure of a tire on a car must be inflated to support the weight of the car. Here's the answer. So the idea here is they give you the contact area of just one tire, each tire. It says each tire, so it's just one tire. But as you know, there are 4 tires that touch the ground on a car, usually. So we're going to take this, multiply by 4 to get the total contact area on the ground, right? So we're going to take, for each tire, it's 0.024, multiply by 4 to get our total contact area. That's 0.096. It's actually a lot harder to write on this than I want it to be. But you get what you pay for. And this was free. So this is the total contact area. Then I'm going to take this number and I'm going to chuck it in there for my area. The force is my 12,500, right? And then I divide my 12,500 by this little area and I get a big gigantic number. And that'll be the gauge pressure for each tire. Yay! Alright guys, we're on to the buoyancy practice problems. Something about an ancient statue lies at the bottom of the ocean, and how much force is going to be needed to lift it. If it's in a fluid, if it's in water, then you may not need as much force to lift it up, right? Because you've got that buoyant force already helping. And so for this one, well, first of all, you have a statue, right? And I can't draw a freaking statue. I don't know. Statue. Whatever. Anyway, how embarrassing. Right? So you have to figure out what are all the forces. These buoyancy problems, the big key to them is drawing a picture that shows all the forces. So on the statue, you have a downward force, right? Which is your weight. That's mg. There's an upward force, and that's the water trying to hold it up, and that's called your buoyant force, FB, or F buoy, or something like. I usually call it FB, right? So you have these two forces. So you got to figure out what those two forces are. Okay, so I solve for the weight first. You take your mass multiplied by gravity, 6860. That's a 6860 newtons. That's my weight going down, 6860. I have a buoyant force trying to hold the statue up, rho GV. Rho is the density of the fluid that it's in, so water, 9.8. This is the volume that the volume of water that the statue displaces. And so I get this number, 2,812. Now, obviously, this thing's it's sunk to the bottom, right? Because the buoyant force is not as strong as the weight. And so, to me, this is a just a simple case of winner minus loser, right? Our net force is the winning force, which is the weight minus the buoyant force. And when you subtract those two, you get some number. Okay, and that number is the amount of force you would need to lift the thing up, right? That is your net force acting on that statue, and it's a down force. And so if you want to lift the thing up, you have to lift up with the same amount of force, right? And so that's your answer. It should be 4,048. Okay, next one. This is our second one on our buoyancy practice problems. A spherically shaped balloon has a radius, is filled with helium. And what's the maximum load the balloon can lift? So, helium is less dense than air, so it will rise, and that's why we use helium in certain applications, and you can get a balloon to actually lift something, right? And so this is a thing. So in order to do this, what I'm going to do first is draw a picture. This is my helium balloon, isn't that cute? And I got to figure out what all the forces are acting on the balloon, right? So of course, everyone can say, all right, well, we have a force going down, right, which is mg. That's the weight of the balloon. The balloon's skin has weight. So even if you sucked all the helium out or sucked all the air out, you'd still have this, this stuff, this material, and it has a weight. There's actually a second weight down. Okay. This is the weight of the helium itself, because gases have mass and have weight. So I have two forces down here. I have an upward force, which is my buoyant force, FB. The heck is the buoyant force from? Well, this balloon is floating in air. So all these little dots I drew out here are air molecules, right? So balloons, like helium balloons, are actually floating in air, just like a boat floats on water. Okay. So there's a buoyant force caused by the air, right? The balloon pushes aside a certain amount of air, okay, just like a boat pushes aside a certain amount of water. So these are my forces. Okay. And I'm trying to calculate the maximum load that this balloon can lift, right? So what I'm going to do is first I'm going to figure out what all these forces are, and then I got to try to figure out what the net force is. Okay. So one of the first things I'm going to do is I'm going to try to calculate the volume that this thing takes up, right? We're going to assume that it's just a sort of a circular shape. So that's volume of like a, is it a circle? Yeah, it's a spherical. Sorry, so it's more of a sphere. So volume of a sphere is 4/3 pi r cubed, right? And that's one of those things. If you don't know that, you have to look it up. And so I'm going to calculate the volume of my sphere first. Okay, so I'm going to calculate my buoyant force. This is my upward force. It's always good to know which way the forces are going. So my buoyant force is rho GV. Rho is the density of the fluid that it's floating in. G is 9.8, which is gravity, and this is the volume that the balloon takes up. So I multiply those three together, I get 45402. That's 45,402 newtons. That's my upward force. Okay, next I got to figure out what is my total weight down. They told us what the weight of the skin of the balloon is. It's 8,300 newtons, right? And then I just got to figure out what is the weight of the helium inside of there. I'll add the two up to get this total weight down. That's my total down force, right? The trick here is that helium, we don't know what the mass of the helium is, right? We know what G is, but we don't know what mass of helium is. So how the heck do we do that? Okay, so what we're going to do is we're going to put something else in here for mass of the helium. We don't know what the mass is, but we know that density is mass divided by volume. If we solve for mass, that'll be density times volume. We can take these two things, density and volume, and stick it in there for mass, right? So what we're going to do here is actually we're going to do rho v g, which is really interesting because that's the buoyant force. So that's the equation for buoyant force, and that's funny. And so we can calculate what the weight is of the helium inside of there just by figuring out what the density and volume is. The volume we know, it's the volume of the balloon, okay? And I think they told us density of helium. Yep, so we know the density of the helium. This is 0.178, so this is 0.178. This is 3591 from here. We know what G is. We add those two things together. We'll get an answer. And the answer is 14,564. 14,564 newtons. That's a 4. Anyway, so that's my total down force. This is my total up force, right? And so to find my net force, net force is winner minus loser. Well, this looks like this is a much bigger force, right? This is my winner. This is my loser. Do winner minus loser, and I should get my 30,838. That number represents the amount of force left over that this balloon could essentially hold, because that's an up force, right? So if we wanted to tie something, here on the end of the string, and it could hold that, because this is an up force. It's an up force. And this is our total down force. That makes sense, right? So when we take these and subtract from this, we have some up left over, and that's the amount that this thing could hold. All right, this is our third and last buoyancy practice problem. This one's about a barge. A barge is essentially just a big, it's like a receptacle, and it floats, and you can put stuff in it. And then you have these things called tugs, and the tugs push the barges around in the water. You have a barge, and they give you the width and the length, and they load the barge up with coal. And so the question is, when they load that thing up with coal, how much water will come up on the side of the barge? What's the height of the water? It comes up on the side of the barge. So I drew my barge here. It's just essentially it's just a square shape. So the question is, what are all the forces here? Well, you have a couple downward forces, right? You have the weight of the barge, itself, and the weight of the coal, and you have an upward force, which is the buoyant force, right? That's FB. So you got to know what all your forces are. You got to know which way they're going. That's the thing. Okay. Now they give you the length and the width because you can either find area or you can find volume or what have you. So we're probably going to do that. All right. So really we're just trying to figure out about the coal, right? They put the coal in here, right? And this thing's going to sink down. It's not going to be submerged because it's not. It's supposed to hold all this stuff. So I find the weight of my coal by doing mg, and I get this gigantic number. That weight has got to be counteracted by what force? This buoyant force. And I think we're including the weight of the barge as well. We're kind of cheating here, so I think that includes the weight of the barge as well. So this total force has to be counteracted by the buoyant. So if I take this number, this weight, and divide by rho g, what I'm left with is volume. So I can take this, divide by rho g, which I know those things, and now I know volume. Volume is length times width times height. And length times width is the area, which I know. So I can solve for height, which that's the answer I need.